Hi again, everyone. So I'm going to be telling you about energy levels in atoms. So we are still talking about quantum phenomena, and today I'm going to be focusing more on excitation, de-excitation, the type of photons you can get in fluorescent tubes. So first of all, I need to tell you how an atom looks like from the inside, okay? Not quite on the detail of the nucleus and the electrons, but just so you know, we have the electrons going around the nucleus in orbitals, okay? So they don't go quite in this super circular shape. They actually have kind of a certain distance from the nucleus where they can be, but they are going to be at certain distances, and each of them have certain energy levels, okay? So we know that the electrons are attracted to the nucleus by the electrostatic force. We know that they move about in the nucleus in specific shells or orbitals, or as I said before, energy levels. And again, these are very specific, so they depend on the atom that I have. The same atom is going to have exactly the same configuration and exactly the same energies in each of the shells, okay, or the orbitals. Different atoms will have different energies that will never be the same as the atom that you spoke about first. So it's kind of an idea, DNA for the atoms, okay? The energy of an electron within the shell is constant. So if the electron is going to be in the first shell, for example, then the energy in that shell is always the same. If it goes on the second shell, the energy level is different, but it's always the same throughout the shell, okay? The shell's energy increases with the distance to the nucleus. So the further away you are from the nucleus, the more energy you need to be that much away from the nucleus that has a positive charge. So you need to have more energy. And then each shell can only hold a certain number of electrons. So you cannot have more than a certain number of electrons in each energy level, okay? The first one can have up to 2 electrons, and then the other ones can hold 8 electrons. So the energy levels, this is an example of the energy levels. So I have here the ground state, I have the excitation energy in the electron volt, and I have the actual energy level in the electron volt. So you can see the ground state has the least energy, and then I keep growing until I can have ionization. So if I happen to meet 10.4 electron volts, my electron can actually leave the atom, okay? The ionization can happen. And again, all these bars, all these red lines, they are going to be the energy levels for this particular atom that I have in there, okay? This particular element, in this case, is mercury. So this is going to be different to other atoms. And as you can see, they are very specific. So the electron is either at 0 or at, let's say, 5 or 4.8 in there, 5.9. So they are going to be very specific of that particular element, all right? I know that I'm saying this over and over again, but this is so important. So the lowest energy state of an atom is called the ground state, okay? So it's when the atom is in the most stable part. If an atom absorbs the energy, one of the electrons moves to a shell at a higher energy level, and we say that the atom is now excited or in the excited state. Now, the energy level diagrams, this diagram that I was just showing you here, they show the allowed energy values for the atom, and each allowed energy corresponds to a certain electron configuration in the atom. So again, one more time, this is very specific for that particular atom, okay? Different atoms of different elements will have a different electron configuration, therefore they will be allowed different energy values. This is what make us know, for example, in a star, or what type of elements the star has, because we look at the absorption and emission lines, and we can figure out where the photon went or where it came from, and we can figure out what are the elements that make that star, because each energy level is going to be a certain, as I told you, DNA, so it's going to be very specific to a certain atom, okay, or element here. So atoms absorb energy when they collide with other, when electrons collide with other electrons inside, okay? But they do not retain the extra energy all the time, so they don't have it forever. This is told in the previous video, so if you don't know what I'm talking about, do go to the previous video, okay? So, gases at low pressure, they will emit light when they are made to conduct electricity. Sorry. So this is because the electron configuration when an atom is excited is unstable, because I have an electron that is not in a certain state, in a lower energy level anymore. The atoms like to be in the lowest energy levels as possible. So the electrons use up the first of the ground state and then the second shell completely and then the other shell. So because that's when they are more stable. So if an electron goes to an outer level, then it means that it's excited and is not in this very stable state, so the atom is going to be unstable, okay? So the electron then moves to an outer shell, leaves a vacancy inside to whichever it goes. It's going to leave a vacancy from wherever it came from, okay? So eventually this vacancy is going to be filled by another electron from an outer shell. So one moves out and the other moves in, okay? When this happens, the electron is going to emit a photon, because if they want to go from an outer shell to an inner shell, they will emit energy, okay? Because they are going to go from an energy level that is higher for an energy level that is lower. So they emit energy in the form of a photon, okay? So they emit the energy and then the atom moves to a lower energy level. And actually here I could have said electron moves to a lower energy level. So the energy of the photon is going to be equal to the energy lost by the electron and therefore the energy lost by the atom. And as I told you, these energies are going to be very, very specific. So the energy emitted, so an atom in an excited state can de-excite to the ground state indirectly. So for example, imagine that I have this photon, this electron in here in the ground state. It goes to the outer shell, second state, and then when it de-excites, it goes back to the ground state. Now, and emits a photon. Now, it could either go straight from the second shell to the ground state, or imagine that instead of being the second shell was in the fourth shell, for example, it could go from the fourth directly to the ground state, or fourth to shell number 3, number 2, and then number 1. Or it could have gone in any other ways. It could go step by step or directly into the ground state, okay? So for example here, a mercury atom at an excitation energy of 5.7 electron volts may de-excite to the 4.9 electron volt, emitting a 0.8 electron volt photon, and then to the ground state from the 4.9 electron volt level, emitting a 4.9 electron volt photon. So it can happen directly or in stages, okay? In general, when an electron moves from an energy level 1 to an energy level 2, the energy of the photon that is going to be emitted is going to be hf, where h is the Planck's constant, f is the frequency of the photon, and that's going to be equal to the difference in the energies of the two states, okay? So, excitation using photons. I can also have an electron in an atom that can absorb a photon and move to an outer shell where there is a vacancy, okay? But this only happens if the energy of the photon is exactly the same as the energy that the electron needs to gain to go there, okay? So, as I said here, equal to the gain in the electron's energy. So the photon energy must be exactly equal to the difference between the final and initial energy atoms, levels of the atom. If the photon's energy is either smaller or larger than the difference between the energy level 1 and 2, then the electron is not going to absorb the photon, and therefore the electron is not going to move to an outer shell, okay? So here I have an example. I would have here 2 electrons. As you can see, one is going from the ground state to the first excited state, and there is an incoming photon that is going to be absorbed by this electron for this electron to actually be able to do so. Because this photon has exactly the same energy as the energy differences between these two shells, then the electron does absorb the photon and can move outwards. Otherwise, this would not happen. And then when you have excitation, you can have a de-excitation. So as I told you before 2 slides ago, an atom in an excited state can de-excite directly or indirectly to the ground state, regardless of how excitation took place. So it doesn't matter if I went from the ground state to the energy level number 3, I can still go down, so from the energy level 3 back to the ground state directly, or by going to the energy level 2 and then 1, or any other route, okay? As long as in total I do the same change in energy. So an atom can absorb photons of certain energies, and then they can emit photons of the same or lesser energies. So for example here, ground state, I get a 5.7 electron volt incoming photon, so I can go straight to this energy level of 5.7 electron volts. I can de-excite by going 5.7 electron volts down, or doing 0.8 to go to the other energy level that is 4.9 electron volts, and then fall 4.9 electron volts back to the ground state. In the same way, I have here, this is exactly the same thing actually. I made a picture twice, so I thought that I had this just once. So again, I could either go directly from the 5.7 to the 0, or then 0.8 and then 4.9. In this example, I emit 2 photons. I could have emitted 1 photon alone of energy 5.7 electron volts. So this is how you can have fluorescence as well, okay? So some substances glow with visible light when absorb the ultraviolet radiation. So the atoms in the substance, they absorb the photons, they are within the ultraviolet region, and they become excited. And then when they de-excite, they emit visible photons. When the source of the ultraviolet radiation is removed, then the substance stops glowing. So they can get a higher energy photon, and then when they de-excite, they can not de-excite from all that energy at once, but in little bits, and then emit a photon that is visible. So this is how we get fluorescence, okay? So the fluorescent tube is going to be a tube with a glass tube with a fluorescent coating on the inner surface. So the tube is going to contain mercury, which is that atom that I was telling you about just a moment ago, and it's going to get mercury vapor at a low pressure, okay? So when the tube is on, it's going to emit visible light, and in case you don't know it yet, this is because there is going to be ionization and excitation of the mercury atoms when they collide with each other and with the electrons in the tube. And then the mercury atoms are going to emit ultraviolet photons as well as visible light photons, and photons of much less energy when they de-excite, so some of them are visible light. Then the ultraviolet photons are absorbed by the atoms of the fluorescent coating, causing further de-excitation of the atoms. And then the coating atoms de-excite and emit visible photons. So if it doesn't happen in the first instance, then it happens later on, okay? So this is how you get fluorescent lights. And these fluorescent tubes, they are much more efficient than filament lamps. For you to have an idea, a typical filament lamp is going to give you 100 watts and is going to, or needs 100 watts of energy input, but it releases about 10 to 15 watts of light energy, so useful output, and wastes all the rest of energy as heat, okay? A fluorescent tube, on the other hand, can produce the same light output with no more than a few watts of power wasted as heat. So efficiency overall is higher when I use fluorescent tubes and I use the excitation and the de-excitation of atoms instead of using the electrons going around in a piece of wire and heating up the wire because of resistance. Okay, so I think it was clear. I hope it was. If it wasn't, just let me know and we'll see what we can do about this. So thank you, and keep tuned for more energy levels and spectra. Bye!